Okay, so as we said, what's up, everyone? How are you guys doing? I'm good. I always don't like the 45-minute sessions. I always feel like they're rushed. As we said, we'll go over the technical stuff of neural networks today, except for the coding part, which we will do on Tuesday, okay? But today I want to go through showing you guys like how neural network works, basically. I know you guys know most of it already. How we train neural networks using backpropagation, some common activation functions, and a little bit, if we have time, about the philosophy of neural network or like ideas that we need to know. And then on Tuesday, we'll do how to code using PyTorch, because that's the one library I kind of know, but there are other libraries. And we will move on to the unsupervised learning, which I understand you've moved on in the lectures already. Okay. All right, so this is part of a file I put in the helpful stuff. The whole file is, yes? The whole file is here, and it's color-coded, very simple, fully connected neural network with two features, X1 and X2. Two features, X1 and X2. One hidden layer of 3 nodes, so there's 3 nodes here, Z1, Z2, and Z3, and a hyperbolic tangent, which I wrote tanh activation function. It's not written anywhere here, but if you go in the document, you'll see that the activation function, which non-linearly transforms the formula from the node in the circle to the node in the square, that's how we did it, is the hyperbolic tangent. And then it has one output only. So this is good for, let's say, a regression or a binary classification problem where you have one output. But if it was a multi-class classification problem, you'd have a lot of outputs, a lot of nodes at the end, right? And then you would do a softmax on them and choose the highest one or one of those, okay? I'm not going to go through the whole document, but I do want to show you. The document kind of breaks it down, but I do want to show you that at the end, we can kind of represent. So we can kind of represent the whole neural network with one line. I'll show you exactly. Zoom out a little. No, I don't think so. Okay, so essentially our y is the hyperbolic tangent of our z. Okay, and another thing, just as a reminder, we said that the number in the top brackets is what layer you're on. Okay, so this is the first layer, so they get z1 in the top brackets, and the number in the bottom is your index inside this layer. So this is the first node or neuron in the first layer. This is the second node in the first layer. This is the third node in the first layer. This is the first node in the second layer. There's only one node, so it's only one of them. Okay, another thing, we had some confusions about the bias term. Do we include it as a node of 1 or not? So in this, I decided not to include it, following the terminology in the 3 blue 1 brown video, which I recommended everyone to watch. So it's added separately. Okay. All right. So we can think of y as being the z1, or the hyperbolic tangent of z1 times b1, which, if we break it down, it's a hyperbolic tangent of b11 of layer 1 times z1, right? So this is also, it's color coded, so hopefully it makes sense. So essentially we take this first node from the first layer and we multiply it by this b plus this times this plus this times this plus the bias term. This is what we have here. And then we do a hyperbolic tangent on it to get to the z, which is our y. Okay, but now we can look inside each one of those z terms and replace them with what they are equal. Each one of them is equal to the hyperbolic tangent of x1 times the corresponding weight plus x2 times the other corresponding weight plus their own bias term. So if we do that, we open it up a little bit. we get this long expression, but this long expression tells us the relationship from y to our x's, or I should say from our x's to our y, okay? And you can imagine, no matter how large a neural network becomes, right? You can stack 100 layers here, doesn't matter. It will just, at the end of the day, if you open it up, it'll just be one long expression. Okay, so you can think of it as a really long stacked function. So sometimes it's called a nested function because you can see it's always like functions within functions. It's always a hyperbolic tangent of a weight times a hyperbolic tangent of other weights times all the way until our x's. Okay, so there's a nesting going on here. There is also a more convenient way, in my opinion, to show it in matrix form, which I'm just going to copy here. But you don't need to know. You should do what you're comfortable with. Let's copy it here. So here it's capital letters, so it means the whole matrix. So Z1 is actually all 3 Z units, okay? And B1 is all these matrices, is the matrix of all these weights, and so on. And maybe I should have copied the whole thing. Yeah, I'll copy that. You don't have to spend too much time on it, but just it's good to show. Right, so we can represent a matrix multiplication. We have our x vector, or it's like a x row. It's like our data point, right? x1, x2 times the B0 matrix. So this is the B0 matrix, which is all the weights. And if you multiply a vector of size 1 times 2 by a matrix of size 2 by 3, you get a 1 by 3 in the layer. We know this from matrix multiplication rule. And this is what we got. We get the 3. And then we take this 1 by 3 matrix, and we add the bias terms, and then we put it under the hyperbolic tangent function, and we get our z's. This parentheses should be here. I see it now. I'll fix it later. And then we take our new z's, which are a 1 by 3 layer, and we multiply it by 3 by 1 matrix, and we get a 1 by 1 output. And then we take the hyperbolic tangent of that one, and we get the y. So that's, again, 1 by 3 over 3 by 1, and we do a tangent of that one plus the bias, and we get the y. Okay? So essentially what I want to show you is that neural networks are a series of matrix multiplications with nonlinear functions in between them, okay? And they can be written as one long function with all the weights, like all the parameters of each step in there, and the x's and our inputs, okay? Any questions about this? No, I feel like it's clear. Why is it good to know? Do we want to do backpropagation first, or do we want to do common activation functions first? Let's do backpropagation first. Backpropagation is how we train our neural network. So how did we train previous models where we didn't have an analytical nice solution? We used gradient descent. What is gradient descent? We take a loss function, and then we find the derivative of the loss function with respect to any of the parameters. And then we take a step size, the size of our learning rate, or size of the step size, in the opposite direction to the slope, right? Because we want to go down our loss function, right? Remember this? So as you can see, we can do the same thing here. We have to define a loss function for the our predicted y and the actual y, right? And then we can see by that loss function and by that loss, we will update each and every one of the weights and the parameters going backwards by taking the derivative of this long function with all the parameters and all the weights in them, each time in regards to a different parameter, right? So first we'll take it in regards to B11 of the first of matrix 1, and then of B11 of matrix 0, and then B, right? We can do that. Then we'll have the whole gradient, which is simply the vector of all our derivatives in regards to each parameter. Remember that the gradient is a nice way to do all the derivatives in one vector instead of going one by one. And then update. Correct? Okay, so it sounds simple. It sounds difficult because the functions get long, but actually becomes really simple with the chain rule. I want to show exactly how it is, and this will also help us on Tuesday when we code. Okay, so the way we break it down in neural networks, we say, first of all, there's a forward pass. Forward pass is how we get from x's to y hat. So we take our x's. If we do full gradient descent, we take all of the data, all of the x's, right? If we do stochastic batch gradient descent, right? We take some batch, remember those? Yeah. And we put them into the network, we multiply, we do the matrix multiplication and the nonlinearity and the matrix multiplication, nonlinearity, and so on and so on and so on, and we get our predicted y hat. Okay? Then we can calculate the loss, the difference between y hat and our prediction. So this is the forward pass. After we had that, we go and we do the backward pass. The backward pass is we update each layer going backwards. So the last layer is updated first. Updated each layer. Let's do layers parameters by its gradient. Should I write explicitly by the derivative of the loss function in regards to each weight? No, we know gradient. We know what gradient is, okay? So essentially, we first of all look at only, this is why it's good to have. So we only look at this formula, which is essentially how we get from our z's in this layer to our y. So it's only like the last layer, the last matrix multiplication. And we have here 3 parameters. Actually, we have 4 parameters because we also have the bias. And we take the derivative of the loss function in regards to those 4 parameters. And we get a gradient of size 4. And we update accordingly. Okay? And that's how we update these 4 parameters. Then, after we do that, we go backwards 1 step. And then we open it up and we have all the other parameters, right? So all the 0th matrix. And then we take the derivative for each one of those parameters and we update them. Okay? So it's like a step by step. However, this becomes easy because of the chain rule of derivatives. Who knows what the chain rule of derivatives is? You guys must know this. I'm going to find it. Okay. Yeah. So essentially, I'm just copying this from someone else's slides. Like this. Essentially means, okay, that doesn't show what the chain rule actually is. Okay, the derivative in regard to something 2 layers backwards is equal to the derivative in regards to 1 layer backward times the derivative of that 1 layer to the other layer backward. Okay, this we know. It's like I think they teach it like if you do sine of, I don't know, cosine of x or something like that. So the derivative of x, this, so you do the derivative of sine and that one times the derivative of cosine, right? It's nested. Okay, so, and because I hope it's clear that either from the way I expanded it here or just from looking at the network, that going backwards will always be exactly like nesting. So we will always apply the chain rule and multiply backwards by the derivative again and again. So there's a lot of good computer code that can be done to make this faster and to help with a lot of redundant computations that you don't need to do, that to multiply a lot of times the same thing. So it's very easy to optimize comparatively. You don't have to take derivatives by the number of parameters. You just have to go one step backward, find the gradient, and then find the gradient one step backward and multiply and so on. Okay. Cool. I actually think I feel like you guys understand this. I don't want to talk about it too long, especially since we only have 30 minutes left. But if you have questions, that was a good time to ask. No questions? You guys know? Yes.
No, but actually, I just really don't understand what is chain rules of derivatives. I'm so sorry. I know that you said it, but I don't
Yes,
know.
yes, yes. No problem. Okay. Maybe some it's in some of the slides. So essentially the chain rule. Yeah, I'll copy this from the slide. I can copy the whole. Okay, so this is taken from some other slide. But what I will want you, not from our course, but what I will want you to see is that the chain rule for a weight that's 3 layers back in regards to the loss function, okay, is equal to the derivative. So the derivative of the weight that's like 3 layers back, let's say, I don't know which weight this one is, will be equal to the derivative of our y hat in regards to our loss function times the derivative of an h, which is, let's say, 1 layer back. I think they're only going 1 layer back. But yeah, I don't know where they got it from. That's why I don't like copying it. Stuff that I didn't go over. But the whole thing is, okay, let's go here. The derivative, let's say we want to update B11 from layer 0, from matrix 0, the B0 matrix, okay? So the derivative of the loss function in regards to B11 to this B will be equal to the derivative of the loss function in regards to y hat, times the derivative of the loss function in regards to this term, times the derivative of the loss function in regards to this term, times the derivative of the loss function in regards to this term, times the derivative of the loss function in regards to this term, and then times the derivative of this function in regards to this term. So because our functions are nested, and because the way derivatives work is that the derivative of a function within a function is equal, like the multiplication of the derivatives, right? So we can just keep multiplying the derivatives backwards and get our slope. Okay, is that more clear?
Yeah, I think so. I think actually it's because I didn't know these things about derivative of nested functions. So this is why
okay. So we should write it down. We should write it down. Let's yeah, we should write it down. I'm gonna hopefully Wikipedia has a good thing of it. Yeah, I'm gonna do this is from copying it from Wikipedia. Let's see that we understand it. The chain rule is a formula that expresses the derivative of the composition of two differential functions, f and g, in terms of the derivatives of f and g. If there's a nested function, f of g of x, okay, so you see it's a nested function, So the derivative of h is the derivative of f by g of x times the derivative of g of x, okay? So it keeps
Okay.
and you can just keep stacking them as long as we want. And we want to have huge, large neural networks, right? So we're going to stack them very long. But it doesn't matter, it's just math. Okay?
Okay, thank you.
Awesome. Okay, I like this. All right, so now we know how to train them. We know the terminology forward pass and backward pass, which honestly, we've been doing the whole time. We've been doing for regressions and whatever. We just didn't call it that way, right? We always went from the x to get the y, compare the predicted y with the actual y, and use the derivative to update, right? It's just, they wanted to call it this way. We can move on and talk about some common activation functions. So what are the activation functions? They're the nonlinear functions which happen within every neuron, within every node. First question, why do we have to have activation functions? So nonlinear. I'll draw a picture because I think this is the best. We take from our node, which is always like the linear summation of weights times the features in the previous node, but then we go to a square, which is like we said, it's a nonlinear activation. So the reason is, if we didn't have any of these nonlinear activation functions, we will just have matrix multiplication the whole way, right? It will be matrix multiplication. And there's a way to show in linear algebra that if you multiply a lot of matrices in a row, you can also find a different matrix which is equivalent. It will give you the equivalent answer because that's a property of linearity that multiply, like you can find, like if you multiply a few in a row, you can find a different matrix which is equivalent to multiplying all of these matrices in a row. And in that sense, if we don't have the nonlinear activations, we're essentially doing only one big, large matrix multiplication, which is exactly what we did with our linear regression, right? So it essentially will always condense or reduce to being one layer. And it will always have the properties of our linear regression, okay? However, when we add these nonlinearities inside, we essentially make it a lot more expressive. You guys remember the word expressive? It can fit functions which are not linear. It can fit shapes which are not linear. We actually have a meaning for these hidden layers. Like we will choose 3 hidden layers, but they will be meaningful because they can't be replaced by like one matrix or one layer. Okay, so that's why they have to be nonlinear. The activation functions, we said that we can use activation functions which we know, like the sigmoid, right? And so on, which can be equivalent to the GLMs. That's why a lot of people say that a neural network is just a stacked GLM, right? A lot of GLM stacked. But there are other activation functions, and I want to just have the picture and go through all of them very briefly, so that's okay with you guys. Yes, this is the picture that I wanted. The perceptron one we know, just right, one here it's 1 or 0, should be 1 or -1, right? The sigmoid function, we also know that one, very nonlinear. The sigmoid function is also very nice because it's differentiable, so we can take the derivative of it at any point. Same as the hyperbolic tangent. The hyperbolic tangent, it goes from -1 to 1. So a lot of people seem to prefer that, so they can get negatives. Right, sigmoid is always between 0 and 1. That's why it's good for probabilities. But it turns out that these functions, for the computer to implement, they take a lot of time. So people want to take a shortcut, which will be other functions that can kind of approximate the nonlinearity, but also don't take a lot of multiplication time. So they invent the ReLU, And the ReLU essentially says, if you're negative, you go to 0. And if you're positive, we get your value is what you are. Okay, so it's like what you are or 0. ReLU, it can also be thought of as a truncating function, which kind of cuts everything negative, makes it 0. Then it turned out people didn't like that because we kind of also want to give some negative value. We don't want all negatives to go to 0, but we don't want to make it a line. So we do a leaky ReLU, which means that you get a different slope if you're negative versus if you're positive. So it's kind of like if you're negative, you're multiplied by, I don't know, let's say 0.1 in this example. And if you're positive, you get yourself, you're multiplied by 1. Okay, so that way we don't get a lot of zeros. We don't, like, all the negatives don't go to 0. Today there's versions of leaky ReLUs with different numbers, not only 0.1. It can be any number. But then people didn't like this so much because it's not differentiable at the point 0. Right, so what do you do if you get 0? Your computer gets stuck because we need to take the derivatives to calculate the gradients and stuff. So there's what's called an ELU, which I forgot what does it stand for? I wonder if someone remembers. Yeah. Exponential linear unit. Oh, thank you. Yeah, I knew the LU is the units. And it turns out it's very similar to leaky ReLU or ReLU, right? But it is differentiable. Like they fixed it, they stitched it together well. Okay. And today, most of the time, people use leaky ReLUs or ELUs. Yeah.
ReLU also has this problem of the singularity at 0.
Yes, of course. Yeah, absolutely.
Everyone, like many people just use ReLU. They don't go to leaky or ReLU.
Yeah, I think today they go to ELU. I think they do. Yeah, you can use ReLU and see. Like, it's not such a big problem. It's only a problem if you get at that exact point, you don't know the 0. It could be that the code that people use fix it for you. They give you some certain like a certain bump either way or something. That way you never reach 0. I don't know exactly, but yeah. Of course, we can use sigmoids and hyperbolic tangents and we'll get fantastic results. Okay, excellent. What I want to say, in previous years, let's say 5-10 years ago, yes.
In which cases would you prefer to have negative values, like in the tangent or?
Yeah, so that's a good question. So in previous years, 5-10 years ago, let's say, there was a lot of like research about which activation functions are better or when do you want to use which and stuff like that. And I feel that today nobody talks about it anymore. They just feel like give it enough nodes, give it enough power, and you'll be okay no matter what you do. So what I just said was true for all the activation functions in all of the hidden layers, except for the activation function on the output layer. Okay, so there used to be like research, like which ones are more efficient or whatever, which ones do you need less parameters maybe because the activation function can give you more information. I think today people don't talk about that anymore, and they're like, just give enough nodes, choose whatever you want. However, for the final activation function, which transforms your final output to Y, you have to choose one which makes sense based on your Y, right? So if your Y is a binary class, so you should do a sigmoid to convert it into probabilities, right? And then you can interpret as the probability of being in that class, and so on. Or you can do a softmax, or you can do other stuff. And your loss function is determined by the difference between your predicted Y and your actual Y. So your loss function should also, like, should also be taken into account. So let's say you classified all your values. You have two classes. It's a binary classifier neural networks, and you classify them as -1 and 1. Okay? So if you do the sigmoid, you know sigmoid goes from 0 to 1. So it's not good for -1 and 1. You have to make all your -1s be 0, and then you have to say that's the probability of being a 1. Okay? But if you do hyperbolic, the hyperbolic tangent, it's actually good. You'll have your loss function from your actual y's, which are 1s and 0, and what the hyperbolic tangent gives you, which, well, I'm sorry, which are 1s and -1, and what the hyperbolic tangent gives you, which is 1 and -1 and somewhere in between. All right, so you have to make sure it's fitted accordingly on the, I like to say it's like stitched accordingly in the last layer. You know what you're, okay? But for the hidden layers, I wouldn't worry about it too much. My recommendation is use leaky relu, works good, or use ELU, or try it differently. And if things are not working, usually I would recommend changing the number of hidden layers and the number of nodes in each layer before changing the activation functions. But it could be that you read a cool paper that says otherwise and you do otherwise, and that also can work, okay? So don't take my word as the final word on it. Awesome. We're done with activation functions, in my opinion. Any questions about those? Yes. This one. Yes.
First one, the first layer.
Yes.
The same activation function, or how do we know when to change it?
Yeah, so that's a good question. So obviously you're allowed to do whatever you want. You can choose, like, this one will be sigmoid, this one will be hyperbolic tangent, this will be relu. You can do whatever you want. However, choose the same one for all of them. That's what most people do, especially for a bulk of layers. And then sometimes you change it in between, but even then, not so much. You just add more layers and you hope it works. The one thing you have to consider is the last activation function, which will fit, which we said will give you the y. So you have to know what your y is and how it's coded and how your loss function is. But yeah, there's a lot of freedom here. You can do whatever you like. I don't know, maybe tomorrow they discover that if you mix it up, the right mix, like you do randomly, I don't know, 20% sigmoids, 80% relus, it works even better. I don't know if they will discover that, but maybe it will. Nobody knows. But today, the feeling I get from people, from articles that I read a little bit, and from people is that they choose the same one for all of them. Usually it's leaky relu, and just hope for the best, and it works. Yeah.
Can we code it like a different isn't the manual test? Because when you code it, it will be the same activation for everything.
So using PyTorch, it will be the same activation for each layer, but let's say you have 3 hidden layers, you can do a sigmoid layer and within the layer. In PyTorch, I don't think you can go. If you do it, you lose the matrix multiplication part. Maybe you could code it. I don't know. I'll have to think about it in code. You could do it, maybe.
Yeah, but manually.
Yeah, it will take more coding time. Definitely. Yeah. Okay. I know it feels like when I took this course, it felt like there's too much freedom with neural networks, right? There's like too many things we can, and that was the talk in the beginning for neural networks in the beginning. Okay, so we'll get to our last point of today, which is like, we'll call it theoretical big ideas or philosophical ideas. We'll say big ideas about. Oh no, we want to do overfitting first. What I will say is that it does feel like there's a lot of like freedom. And that's because neural networks are an active area of research, and people in computer science buildings are still researching what's better, what's going, So we don't know. In 20 years, we will have answers to all these questions, I'm sure. But as of now, we don't know yet. Okay, so I will write the first big idea is that's an active area of research. Okay, now we'll go to how to avoid overfitting. We'll do it in 5 minutes. Neural networks, just like decision trees, are very prone to overfit. They're very expressive, right? They're very good. Remember, overfitting means that you get a good score on your data because it trains on the particular data sample that you have and it doesn't generalize well, right? Because they're so expressive, they're very good at overfitting. They will tend to overfit. So what do we do to combat overfitting? So there are three classical methods, and then there's one controversial method. No, it's not controversial. It's like let's say it's a questionable method, which we'll talk about. So the three classical methods. The first one is similar to pruning in decision trees, where we cut some of the leaves, remember, in branches. So it's called dropout, and it's where we drop some of the neurons. Okay, so some of the neurons, either randomly or neurons that get values close to 0 or something like that, get dropped. Okay, and there's a picture of it on one of the slides. That the values of the weights are dropped. Yeah. Randomly deactivate some neurons with probability p. So it's the weight, if the weights that are connected to these neurons are close to 0, then that means that neuron is not that important, right? Because all the weights are multiplied. So we can drop it, or we can randomly drop it. Randomly drop some. So the picture here, they randomly dropped a lot of the neurons in this picture. Many of them. Yeah, right? They dropped half. Am I going crazy? Yeah, half. Wow, that's crazy. No, you don't want to drop half. You want to drop a few. Okay. I don't know, like 5%, 10%. See what works. Okay, the second is we're also familiar with it. It's looking at the train loss test curve, loss curve. Okay. Train loss test loss. So what it is every let's say 100 iterations or whatever, you do the loss on your training set and the loss on your test set. So in the beginning, as your model learns, they both have to go down, right? They both have to improve. The loss goes down. And then at a certain point, you kind of reach the point where your loss on the test set is maximal, and then it will not improve anymore, but your model will start overfitting, so the loss on the training set will get smaller and smaller. However, once it overfitted, then the loss on the test set will actually go higher, because we reach the point where we are past the maximal loss, the minimal loss for the test set, and we can only improve by improving on the training set, which actually hurts us on the test set. So there's a nice curve. I saw a picture of it. Yeah. Wait just a second. I want to explain this. Would like to explain this picture. So in the beginning, your train error and your test error both drop until you reach a point where your training error keeps dropping because you're overfitting, but your test error is actually getting higher because you're overfitting. So you stop at that point. Okay, so that's called early stopping, or there's like tricks. If you see that your test score hasn't improved in the last 300 iterations, you stop there, or called all kinds of tricks like that. Okay. Then, yeah, I saw that you talked in the slides about data augmentation, which, okay, I'll talk about it. Another, we didn't talk about it yet, but this can also be done to avoid overfitting in all other models that we learned. Okay. Essentially, if you're worried that you're overfitting to the particular data that you have, so take the data that you have and then change it randomly a little bit. Okay. And that way you will have more synthetic data, false data, which is a little bit augmented, which is similar to the data that you have, but not exactly the same, and add it to the training set. And then your training set will A, be much, much bigger. That's good. And B, it will not be prone to overfit on the particular data that you put it for the training set, because it has a lot of instances which are like similar but slightly different. So this in computer vision, they like to do it. They like to take the picture. Crazy. They like to take the picture, the image, and then they kind of crop it or change the lighting a little bit or change the, so you see, you take, instead of just putting that original image, you kind of flip it and you rotate it and you blur it maybe and you make it brighter or darker or whatever. And you add all these instances to your data set, to your training data. And that way you're not prone to overfit on this original image, but you're actually good at, seeing cats, even when it's a little brighter or a little darker or when they're rotated or so on. Okay. Yes.
And for data that are not images, how would you augment it?
So for every feature, add some noise to it. Let's say your height feature. So add 2 centimeters here, 3 centimeters here. You have to know what the particular feature is, right? And then you have to kind of assume what things of the feature can change a little bit without affecting the Y, and change those. Okay, but usually you add like a random noise to it, like from usually even you say a normal distribution around it and you add it. Yeah.
So it's not like you're adding more random data, but you're transforming yours?
No, you are taking your data and you're doing a lot of transformations on them, and each one you're adding it to the data. So you are adding. So here you're adding 10 times as many pictures. Each one is a transformation of your own. Yeah. 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 Okay, now we'll talk about the fourth controversial method. It's not controversial, questionable method. And then we'll talk about the big ideas. Okay. And we'll finish 5 minutes late than usual. First one is, the last one is how to not overfit on your data that doesn't generalize well. So the root problem of overfitting is that your data is representative, but it's not fully representative of the population of your test data. So your training data is not fully representative by the test set data. So we train on the particular of the training data, and then we find a test data point that is not similar or not similar enough to our training set, and then we don't know what we're doing on it. Okay. This is also called the problem of extrapolation, to extrapolate from our limited sample into the whole population, which can contain all the samples, right? So the people said that we can allow overfitting, but to include, I'm writing all the data in the training set. Essentially, what we say is we're like, okay, we'll allow the model to overfit on our training set, but we will make sure our training set will contain every possible data that we can have. That way, no matter what new data you give me, it's already been in the training set. So I'm overfit on it. Okay. So it's like a method of using these big guns as they are, like big guns. And this has been very questionable. People said it will not work. People will always find examples outside of the training data. But this is what people like GPT, for example, that's what it did. It literally took all the internet, right? I don't know how much of the internet they don't tell us what went into the training data, but it's obviously, all of Wikipedia and all of GitHub and all of forums and Reddit and whatever, and Facebook and everything. I don't know if they have Facebook, but whatever. And they just fit on it. And in a way, they didn't really care so much for overfitting, because they said, yeah, we're overfitting on the English language, but we're going to have enough of the English language that every new thing that you ask me, it's already seen something very, very similar to it already on the internet. So it knows what to do. Okay. So that's why most of the coding problems that you ask ChatGPT to give you a solution, it's not giving you a solution. It's seen the problem that you already asked it, and it knows what the solution is. It's more like a search engine in a way. Okay. So it is overfit on the data, just overfit on enough data that it has nowhere to extrapolate to. Okay. And this solution has been called interpolation instead of extrapolation. Okay. Right. So I don't know. They don't tell exactly how they do it, but they say we'll perform well on the test set because we'll have so much data in the training set that the test set will also be very like in there or very similarly to be in there. Like we're not worried about examples in the test set that we haven't seen before. Okay. So it's like a different mentality. All right. So now I will say,
is it a bit like if we were thinking that the big amount of data actually represents the reality, if I can say? Like,
yeah,
much data, so we overfit on the reality. So we cannot miss some examples because they are all in the data.
yeah, so that's basically the thinking. The thinking is this: instead of trying to learn what I'll make it concrete. Instead of trying to learn what a cat looks like from 1,000 pictures of cats, we'll learn what a cat looks like from millions of pictures of cats, or from pictures of every type of breed of every cat in every angle that we can find, in any lighting position that we can find. And then whatever picture you give me, I already know that it's a cat because I've been overfit on the training data, but it's been on the training data. Okay, so it's like that's the thinking. Yeah, there's a big question. So obviously the upsides of it that it works. We see these large models working, right? GPT or whatever. The downside is that you do need loads of data. And data collection is very, very difficult. And a lot of training time, obviously, and a lot of parameters and so on. I will finish by saying the big ideas that we need to remember about neural networks. Yes.
How much is enough to allow this?
So for pictures, I know they have, they don't release how much they have, but I know they have at least 70 million pictures in their data set. Yes. You can look it up, what it is. For text, they don't release it, but it's like loads. Yeah. It's something none of us can do in our computers. We need a lot of, yeah. Okay, so I'm going to finish the big ideas. The big ideas about it's an active area of research, literally. So that means it could be that next year or in 2 years, we will have completely different conclusions. We will have, I'm writing, it's very easy to modify the architecture or to tweak our, so the network I showed you today, it's called a fully connected neural network because every node is connected to every other node in the next layer. But you can make tweaks. You can imagine about tweaks about some nodes connecting, some not connecting, or adding recurrent connections, which are next connections go higher layer to lower layers, or other stuff like that. And you get a lot of the modern architectures like the convolutional neural networks or even the transformer neural networks, which are popular today. So yeah, it's very easy if we get these basics to just add and tweak on. Also, I should say they're not generative. Remember, generative is that when you can give it a label and it will give you back a fake data. So neural networks are not generative, but it's very easy to turn them into generative. We'll show this towards the end of the course. Okay. Also, scaling works. So I'll just make making them bigger works. So, and it works in surprising ways. So sometimes you think, oh, I'll just make them bigger, more layers, more features, and it will just be a little bit more accurate. But sometimes, for example, with the language models like GPT, you have to make them past a certain size and then they show a really big improvement. Like there was some sort of bottleneck at a certain size, and then you make them bigger, and they can suddenly do things which the model at the previous size could not do. So the way that the scale and the size of the model and its inner architecture help us predict our Y is very, let's say, it's not easy to predict. It's mysterious. We don't know exactly how it works, but making the bigger usually works. Of course, they will also overfit more. Okay. And then there's a question of they are not okay. Interpretability. Remember we talked about interpretability for previous models. So interpretability is like, do we understand why the model predicted what it predicted, and do we understand how important is each feature to our model? And in neural networks, they're not interpretable. That's a big downside of them. They give you the number Y at the end, but you don't know why they gave that number. You can look inside all the matrix multiplications and see all the matrix multiplications that did along the way, but it doesn't help us understand why. Interpretability right now is probably the most active area of research in neural networks, besides just making them more efficient. And there are lots of cool new methods to try to, yes, understand the relative importance of features and so on. I don't think we're going to be talking about it so much this course, but it's actually a big area of research here in Bar-Ilan. So once the semester starts or whatever, we will have probably guest lectures about that and stuff, if not here in the computer science department for sure. So just so we know. So these are the first really non-interpretable models that we encountered, and that's a downside, but people are working on it. Okay. And what else did I want to say? There's one last point. I had 5. Oh, okay. Yes. It's an important point. I'm sorry that I'm taking long, but we'll be okay. There is a different way to think of neural networks, which doesn't change the math at all, but it does change the way we think about them. So remember that the neural network is kind of a stacked, functions, or we have layers. Here's what I'm going to say. Remember, in SVMs, we use the kernel trick to take our data of size 2 and to project it into a higher dimension. So we'll have data of size 3, like 3 features, including in the projected dimension. And then we can have the linear separator in the high dimension. So in essence, what we did is we took our data points and we projected them to higher dimensions, and then we did our division, separation, and the higher dimensions. In neural networks, a different way to think about them is that they take the data points, and each layer is a projection to another dimension. It could be a higher dimension, in this case it is, and it could also be a lower dimension. You can take, you can go from layer of size 3 to a layer of size 2, right? And you can make them lower or higher. And so, in essence, you can, instead of thinking about it as stacked matrix multiplications or stacked functions, you can also think of them as stacked projections to other dimensions. And it kind of finds the best projection in each dimension to allow it at the end to have the least loss. So these projections are very useful. For example, let's say you have a data of size 2, right? But you want to have a size 3 projection of the data that kind of maximizes the information about the outcome. You can train a whole neural network, have it have the least loss, the Y has the least loss, and then use this layer of size 3 as your projection in the 3-dimensional projection of your data of size 2. You can take a new point, a new data point, it will have 2 features. You input it into your trained model, you see what the values are, what these 3 values are, and you can treat them as a projection, a 3-dimensional projection of your 2 points, which maximizes information about the Y in some sense, okay? So I'm writing here, they can be thought about as a series of projecting our data to different dimensions. Very useful, which is very useful for us later on. Okay. Yeah, you choose what layer you want. So yeah, you can choose. You can go higher and then lower. You can do whatever you want. If it's for lower dimensions, it's actually a dimensionality reduction method, right? If it's for higher dimensions, like the kernel trick in SVMs, right? It's very, I will write another line that the whole a trained model can be useful in many ways besides prediction. Okay, so this is kind of continuing the line that it's a series of projecting. If you have a trained neural network model, you can use it in many ways besides just projecting the next Y. For example, projecting the data and so on. So yes, it's a good thing. So even if you don't ever want to train your own neural network model, or you feel like you can't compete with Google and OpenAI and whatever, if you can take a neural network model that's already been trained, you can use it for many things besides what it was trained for. There's information encapsulated in there. You can use it as a dimensionality reduction or dimensionality expansion, or even for other stuff. This can be helpful in neuroscience as well. A lot of people take trained neural networks and compare them with the brain, or use them to learn about the brain. Okay, so that's a big idea that I want you guys to have. All right, we're done. Any questions?